Okay, so we continue with okay, we wait a while for the recording. Okay, so we continue with the study of lecture 3 in session 2. You remember session 2 is about the study of automation, and we use industrial automation as a background to support the learning. So in lecture 1, we know that the manufacturing consists of design, production, and the marketing and the sales. Inside the production, we have an input, we have an output, we have a lot of inner process, all right, which will transform an input to the output, all right? So lecture 1 gives you an overview about the manufacturing system, all right? So in lecture 2, we zoom in into some typical process inside the production line. All right, and then our focus is to identify the key parameter, the variable, key variable, which should be under control. That gives us opportunity to implement automation system. All right, automation system means what? To make the control of a certain parameter, certain variable to be automatic. All right, so lecture 1 is for us to know what is manufacturing, okay? What is the production line system? There are a little bit of mathematics involved. Lecture 2 is for you to know, okay? Inside some typical process, what are the key variable, key parameter, okay, which need to be under control. But the good news is among all the typical example of a process, you see the presence of doing motion control. All right, then how to produce a motion? You know that usually we use actuator, motor. Therefore, if you understand how to control a motor, eventually you are ready to control all the other parameters inside a process. All right, because temperature control is quite straightforward, force control is quite straightforward, and pressure is related to the force, all right? It's quite straightforward because if you look at all the process among all the controllable variable or parameter, basically we know we need to control motion, temperature, force, and the timing. All right, so you see the force are more or less present everywhere. The motion are present in all the process. All right. Then behind the control of the motion, basically it is a control of the motor. All right. So in lecture 3, we just give you the basic understanding about the design of a motion control system. Okay, focus on the motion control of actuator or electric motor. All right, with this knowledge, you should be able to apply it to the control of temperature, control of timing, control of the force, etc. All right, clear? Okay, so we continue. And another thing is for you to know is normally you need to spend 1 semester to study control theory. I'm going to summarize the key knowledge in control theory within 1 hour. All right. So you see the benefit for you to attend this course within 1 hour. All right. More or less you have been exposed to the key concept or key principle inside control theory. All right. Okay. So I try to make you understand that. All right. Okay. So section 2 is for us to study automation. and in the context of manufacturing, all right? Because manufacturing is very important for our economy, and the manufacturing include design, production, and marketing and the sale. And inside the production, we have a lot of process which allow us to transform input into the output, all right? And here, pay attention by default, when we talk about the manufacturing, we talk about the mechanical manufacturing, all right? They are chemical manufacturing, biological manufacturing, all right? Okay, by default, we focus on manufacturing, mechanical manufacturing, okay? So that is the background knowledge. And in lecture 1, we understand what is the manufacturing. In lecture 2, we understand what are the possible parameter and the variable which could be under control automatically, all right? Now, we zoom into the answer to this question, how to automatically control any specific parameter. And here we use motion as an example, all right? So this is the outline of this lecture 3. So we just quickly summarize the process under control. Then we just pick up, okay, motion from actuator as an example. Then go through the way how to design the controller, all right? So within 1 hour, you will be exposed to the more or less entire theory in controller, all right? Okay, so we move on. So in lecture 2, we have gone through all the major typical process in manufacturing. Then here, I just give you a quick summary. Okay, so you know what is a welding, right? So you have seen it. What is a painting? And you have seen it. So from here, you see the motion, all right? Just keep this idea in mind. Okay, the dominant parameter, dominant variable in industry are motion-related variable, motion-related parameter, all right? So these are the dominant parameter, okay? And what are the motion-related variable or parameter? Basically is what? Position, velocity, acceleration. That's it, very simple, all right? And then in lecture 2, we know they are solidification process, okay? Injection motion is one typical example. We also have a deformation process, all right? And the rolling is a typical example. We know all this, right? We also have a material removal process, all right? So then the turning and the grinding, all right, material removal. So this is a typical way to remove material layer by layer, all right? And here you will see we need to control the motion of the cutter, okay, the velocities, the depths, etc. All right, so you keep all this in mind. Then for the joining process, we know that we use welding to join 2 workpieces together permanently, etc. All right. Then among all these 4 typical processes, we understand that the motion control is the dominant one. If we understand motion control, it means what? We understand everything, all right? So this is why we zoom into motion control, all right? Then since motion is being provided by motor or actuator, then we need to know what is the mathematical description of a motor or actuator. Then from there, then we can design the controller and to design the feedback control loop, all right? So you see motor not only present in all kinds of manufacturing equipment, it also present inside the robot itself, all right? For example, for a robotic arm with a 6 joint, then inside we have a 6 motor, all right? So therefore it's meaningful for us to focus on the control of a motor. If you know how to control the motor, eventually you know how to control everything. All right, understand? Okay, so then what is a motor? Actually, motor is a mechatronic device, or because it's an electronic device, because we can, if motor will take electric energy as an input. Motor is also a mechanic device because it output mechanical energy. So therefore, it is a mechatronic device. All right. So input, you see, this is a circuit for the input. It's very simple. We apply the current which goes through the coin in order to produce a magnetic field. The magnetic field will interact with the permanent magnetic field, then create interaction force. Then this interaction force will make these two rigid body to undergo relative motion. Because inside the motor, we can talk about the one rigid body under the name of a stator, another rigid body under the name of a rotor. All right. So in generic term, you just say there are two rigid body, and these two rigid body has its own magnetic field. When there's two magnetic field, then there's interaction force. All right. So one rigid body refer to rotor, another rigid body refer to stator. Very simple. All right. Conceptually. All right. So input is electric energy, output is mechanical energy. Then for at the electronic side, then you will see the applied voltage, all right, is equal to the voltage across the resistor, equal to the voltage across the inductor. Coin is an inductor, right? When the inductor, the coin rotate inside the magnetic field, it will generate electricity. All right, it's like this is the principle of electricity generation. I guess in year one's physics, you know this principle, all right? But in mathematical terms, we call this voltage produced by the coin inside the rotating magnetic field as an electromotive force, because this voltage will cancel out the effect of the applied voltage, all right? So that means the applied voltage is equal to the sum of these three voltage. That is a behavior in the electronic side. And the good news is the voltage produced by rotating coin is proportional to the rotating velocity of the coin. Then you see this equation relate variable in electric domain to variable in magnetic domain, because the velocity, Q dot is angular velocity, all right, in magnetic domain, all right? Now we look at the magnetic domain. So once we have a magnetic force, then the rotor will receive a torque, okay? Then this torque actually is proportional to the current which flow inside the coin. So this is the motor constant, we call it. So the torque output from the rotor proportional to the current, all right? Then we rewrite this equation. Then we can say current is proportional to the torque produced by the rotor, all right? And then we derive a derivative equation, just compute first order derivative. Then we have this relationship. Then you see this is very simple, all right? Now we try to replace, substitute I, because here you have a I. For inductor, you know, okay, variation of the current pass through the coin will produce a voltage, right? So this is an equation of an inductor, equation of a resistor, all right? So these are the basic mathematics. Now we can combine all these equations together to come out as equation which relate voltage to the two important parameters in magnetic domain, all right? So this one is a torque, and another is angular velocity, all right? So this describes the behavior of actuator. Now we want to know, okay, in order to produce, for example, this velocity, what should be the applied voltage? Because this is a differential equation. How to solve differential equation efficiently? The good news is Laplace transform in frequency domain, because in time domain it's quite difficult for us to solve a differential equation, right? So, but it will be extremely easier for us to solve differential equation in frequency domain, all right? So if we do Laplace transform, then this equation will become simple, right? So that is a motivation for us to do the design of a control system in frequency domain, but not in time domain, all right? So this slide gives you this motivation. This is why you need to know this beautiful tool for the study of a control theory. That is a Laplace transform. So therefore, then you see you need to spend some lecture to study what is a Laplace transform. So here I just show you the result of a Laplace transform. And the first thing for you to know is Laplace transform make use of vector as a variable in frequency domain. All right, this vector is called as a S. All right, but in textbook they use this terminology of a complex number, because complex number may cause confusion to many students. All right, so here I recommend you to just visualize complex number, translate it into a vector in frequency domain, because S is a vector which has a horizontal component and a vertical component. All right, so sigma is the horizontal component, omega is a vertical component. All right, so and the discovery of a Laplace transform or invention of a Laplace transform has benefited from this beautiful equation discovered by this famous scientist or mathematician under the name of Euler. This is a Euler equation, very beautiful. Actually, J was invented by Euler. All right, so J does not exist. J is equal to square root -1. All right, it is an imaginary space or imaginary dimension. All right, and for those of you who know religion, people may say this is a space indicate in the in the heaven. All right, in the sky. All right, so Euler basically use this equation, bridge the gap between our world and the world of in the sky, in the heaven, etc. Right. So anyway, this is a very beautiful equation, and the biggest contribution from Euler is this invention of a J operator. Right. Then with the use of a J, then we can define S vector. With the definition of a S vector, then we can come out the Laplace transform. All right. So then we have a two-dimensional space for S. We call S plane. Then S is a vector. Then very simple. Then that's it. Then Laplace is a French scientist discover this forward transform, inverse transform. Okay. If you have a time function ft, you do this integration, then you get the frequency function. If you have a frequency function like this, you do this integration, you recover time domain function. So it's very beautiful. Then you may say, this is a very complicated computation, but good news is we can calculate all this and put into the lookup table. And there's also some simple rule for us to follow so that we can easily determine inverse Laplace transform forward Laplace transform. All right. So this is a very beautiful mathematics. And in addition, there are two useful theorems. One is to predict what is the initial value in time domain if we are in frequency domain. That means this is a magic journal. In frequency domain, without going back to time domain, we are able to predict initial value in time domain and also final value in time domain. So these are the two useful theorems, especially the final value theorem, because the final value in time domain means what? Steady state response. Okay, in control theory terminology, the output is being divided into two: steady state response and the transient response. So final value is a steady state response. That means in frequency domain we can predict a steady state response. All right, so this is a magic result. All right, so like what I say, you understand. In manufacturing environment, inside the production line, the dominant parameter or variable come from motion, and the motion come from motor because motor produces a motion. If you understand the answer to this question or the behavior or description or control of a motor, it means what? You are ready to control entire world. All right, everything in the world. All right, okay. So then, what is the device which produces a motion? Answer: motor. All right. So motor has a rotor, has a stator, and the rotor is connected to the shaft. Then shaft will connect to the payload. This payload can be anything. Can be a production line, can be body of AGV, can be the way of the link, etc. So could be flywheel, okay? So this just example, you just say this is any payload, right? So then we want to know what is the Laplace transform of this motor, and in frequency domain, what is the ratio between output of a motor and the input of the motor. So in frequency domain, the ratio between output and the input is called as a transfer function. All right. So that is another concept. It's quite easier mathematically. It's just the ratio between Laplace transform of output and the Laplace transform of input. That's it. All right. Then you use this one to find out, okay, if input is a constant, the torque, then what should be the time function for the output? Okay, this is just a simple exercise. Okay, so I just go through this one, help you to understand the way how to analyze the system under control in control theory. So I guess this equation should be straightforward to you. Okay, this is the application of Newton's second law. So we have applied the torque, overcome the viscous friction. Viscous friction is proportional to velocity. Then remaining energy will contribute to the acceleration of this mass. Since this is a rotary motion, then we talk about the angular acceleration. Then this is the moment of the inertia of the mass. All right. So it's quite straightforward. Then this is angular velocity. We use omega dot. Omega is angular velocity. Then we have this one. Then we apply Laplace transform. This is time domain. There's one rule for you to know. Okay. Once you see the derivative, like in frequency domain is just S times the Laplace transform of omega. You see, very simple. When you see the first order derivative, then is S. Second order derivative is S squared. Finish. All right. So simple. All right. Okay. Then from here, you can compute the ratio between the Laplace transform of output. Omega is the velocity, is output, and the Laplace transform of input is applied the torque. Then you see it's very simple relationship. It's a ratio between two polynomial, and inside polynomial is what? Addition, multiplication, subtraction, division. All right. So then you see the mathematics description become a primary school mathematics journal. In primary school, we know what is addition, what is multiplication, what is division, what is subtraction. All right. So you see the beauty of Laplace transform to transform very complicated differential equation into primary school mathematics. All right. So then this is why then this conclusion will motivate you to study Laplace transform. For those of you, if you do not know what is a Laplace transform. All right. So it's a very powerful tool, all right? Will make your life much, much easier, okay? Now what happens if the input is a constant? Then for this constant in time domain, we can still calculate what is the constant in frequency domain. Okay, you just divide this constant by S, that's it. Because this is a fixed property, all right? So if you have a unit step response, this is terminology in control theory, you just think input is a constant, all right? Then in frequency equation is constant divided by S, right? Then since we know the ratio between Laplace transform of output, Laplace transform of input, okay, then Laplace transform output is equal to the ratio times Laplace transform of the input. So this is called as a transfer function, okay? And do simplification, then this one is equal to this one. We call this as a partial fraction expansion. You can easily verify, all right? So you merge these two together, then you should be able to get this one, all right? How to obtain this one? Actually, you just name it as A divided by S, B divided by S plus 0. Then how to determine A? Then both sides times S. Then that S equal to 0, then you will get the A. How to determine B? Both sides times denominator on the B is here. Then both sides times S plus 0, 1. Then let S equal to negative 0, 1. All right. Then you should be able to obtain B. Once you have this expression, then immediately you apply inverse Laplace transform. You see 1 over S correspond to a constant. Then 10 over S equal to 10. That's it. All right. Then here actually is equal to 10 divided by S when S undergo a shift. When S do a shift in frequency domain, it means in time domain, you just have an exponential function raised to the power, which is equal to 0.1 times t. 0.1 is equal to the shift. Very simple, because you just treat it as a 10 divided by S with a shift in S. The S will shift by 0.1, all right? Then 10 divided by S in time domain is equal to 10. Because there is a shift, then you add in this exponential function raised to the power, which is equal to 0.1, negative 0.1 t. Done already, okay? This is a frequency domain equation, and then this is time domain equation, all right? So, and when t go to infinity, then you get the steady state response, all right? So it's very, very simple mathematics. I guess you do not need to study control theory. By now, you should be able to follow this slide, all right? So if you know this slide, actually, you know a lot in control theory already, all right? So magic, okay? So in previous example, you know what is a transfer function. Conceptually, it's very simple, right? But here you need to know additional knowledge. This is very simple, but extremely useful for those of you in future, if you want to do AI or do study neural network and deep learning. LTI, okay, linear time invariant system. So it means if you have an LTI system, that means if you have an input X, then you will produce Y. If you scale up, scale down X by A, then the output will be equally scale up, scale down by A. That's it. Most importantly is this one, okay? So if X1 produce Y1, X2 produce Y2, then X1 plus X2 will produce Y1 plus Y2. So it means this is a multiple input channel. We have two input. Then there's a concept of MI, multiple input. Here you have two output. Then there's a concept in control theory called MO, multiple output. So with the LTI system, so it means MIMO system is equal to the sum of SISO system. This is a SISO system, single input, single output, because here tell you single input X1 will produce single output Y1. Single input X2 will produce single output Y2. So it means this MIMO system is equivalent to two SISO system. One is between X1 and Y1, another is between X2, Y2. Okay, so this is very important. So it means for any complicated system, such as MIMO system, we always try to represent it as a SISO system or MISO system, multiple input, single output. That is an important recommendation from control theory, all right? But the thing is, I just let you know, people doing AI, doing machine learning, do not know this important recommendation, all right? So these are just additional knowledge that you don't know, okay? So etc. Then with LTI system, there is always Laplace transform, all right? So then if you have a system, then you see in time domain, if you want to compute output, you must do convolution. In frequency domain, because there's a Laplace transfer there's a transfer function, then Laplace transform of output is equal to transfer function times Laplace transform of input. You see, this is what multiplication. So you see, in frequency domain, we just need to know primary school mathematics, then we can handle everything. However, in time domain, you see, this is very complicated computation, all right? So that motivates you to study or to use the Laplace transform as much as you can, all right? Then this is definition of a transfer function. Basically, it's a ratio between the Laplace transform of output, Laplace transform of input, etc. All right? Then with use of a transfer function, we can graphically visualize any complex control system, all right? It's like this professor use his hand to control this flexible stick, then control this joystick. This joystick control this two finger robotic hand, this 2-finger robotic hand control another flexible stick, etc. And in frequency domain, because we have a transfer function, we can write down all the transfer function in series, then time them together, done already. However, in time domain, I guess it will be big headache for you to derive a relationship function, almost impossible, right? Then you see, with the transfer function is straightforward, all right? So, okay, so the only the first equation that you need to remember in control theory is this one, okay? Because for a single module, it's easier that we have a transfer function. How about this closed loop? This is a standard closed loop. Standard closed loop means there's no signal leak out, there's no external signal enter. Because all this line you must consider as a signal. Because the Laplace transform, basically, you keep this concept in mind, a signal, all right? Because the value is a measurement of a signal, all right? So think this way, energy signal, all right? So then all this line basically is a signal line, all right? So then we can talk about that there's no leak of a signal, there's no additional signal enter inside the loop. This is called as a standard loop. With this standard loop, what should be the equivalent transfer function, right? This is the first equation you need to remember, all right? So the answer is the transfer function of a closed loop equal to the Laplace transform of a forward branch. This is the forward branch divided by 1 minus Laplace transform of a loop transfer function, okay? So it's quite easier. And since we know the transfer function of this one, then just time them together. Then the loops one is what? Is this one times this one times this one. Pay attention here, because here is to calculate the difference. Then this is a negative. So then the loop transfer function is negative. Normally 1 minus negative will become 1 plus, okay? Something like that, all right? So here I just showing you example, all right? So then what is the transfer function of this loop? So forward branch is G1, loop is G1, negative G1, G2, 1 minus negative G1, G2 is 1 plus, done already, all right? Then for this one, forward branch is G1, G1, what is loop? G1, G1 times negative 1. 1 minus negative 1, G1, G1 is 1 plus G1, G1, all right? Then these two is connected in series, then times them together, done already. It's quite straightforward, all right? And with transfer function, we can draw the block diagram. Here you see we can visualize a transfer function, all right? So then what is the block diagram? Then for each module, we just derive a transfer function. Then we draw the relationship among the signal, okay? These signal come from the output of all this module, and they could become an input to some of the module, all right? So the signal to the input, signal from the output of all these module could be connected together. So you treat it as a signal diagram, okay? That will help you to understand a lot of things, all right? So this is, for example, this is a visualization of a very complicated control system, all right? So then we want to know what is the equivalent transfer function between the final output and the final input. The good news is without the writing equation, okay, we just follow the relationship among the signal. As long as the relationship among the signal is unchanged, we can modify this block diagram, all right? So keep the relationship constant. That is good enough, all right? For example, here we have a summation. Summation, we can swap summation. It's like 1 plus 1, 1 plus 2 plus 3 is equal to 1 plus 3 plus 2 is also equal to 3 plus 2 plus 1. Yes or no? 1 plus 2 plus 3 equal to 3 plus 1 plus 2 equal to 2 plus 1 plus 3. It means we can swap summation, okay? So here basically is a summation. Or plus minus is the same, plus negative value. So that means we can swap, okay? Swap this one, nothing change, all right? And this here you see, there's a leak of a signal from here. Because this signal will also appear here, then we let this module to take a signal from here. And this signal is equal to this signal times G1. If you take this signal, then you let this signal divide by G2 or G2, all right? Then they use the result to be the input to H1 module, right? So this way to ship this line, this signal line downstream, all right? Okay, so instead of pick up a signal from here, you pick up another version of the same signal. It's G2 times this one. Since this is G2 times this signal, then you divide by G2, then you get the original signal, right? Then take it as an input. Then in this case, output from this module will remain unchanged. It's the same, right? But the good news is here is this has become a standard feedback control loop. Then we replace it by the equivalent transfer function for this inner loop, all right, control loop. So it's forward branch divided by 1 minus loop. Okay. Then here you see the signal pass through this one, then signal pass through this one, then the A together. This is just a summation. Okay. So then we can easily replace this one by the, because here you just imagine you have a 1, because this signal pass through here, appear here. It's like times 1. So it's 1 plus this. Okay. Then again, this is what standard transfer function. So replace it by the equivalent transfer function. Forward branch 1 minus loop transfer function. Then you get this one. Okay. Then here you have a standard feedback control loop. Then replace it by forward branch transfer function 1 minus loop transfer function. Simplify it, you get this one. Done already. So you see, you simplify the block diagram, you get the final transfer function. So this is really very powerful tool, all right? But the biggest benefit is for us to design the control system, all right? Because inside the robot, inside any machine, you always have this feedback control loop for position, for velocity. So it is present everywhere inside automated equipment in manufacturing, all right? So then we want to know, okay, what is the purpose of doing control? Why not just use original equipment? The answer is, in general, original equipment may not produce a good performance in terms of stability, response time, response accuracy. And also remember in lecture 1, yesterday in lecture 1, when we talk about the system, I tell you to remember that the best system in the universe are static systems. We want the dynamic system to behave as much as possible like a static system. This is why we need to do the control. This is the only way for us to make a dynamic system to behave like a static system as much as we can. All right, that is the motivation behind the control, because we can achieve 100% stability, 100% accuracy, and a very short response time. All right, so understand. So with the initial system, you cannot achieve this result, but with control, we add in the controller, then we can achieve this result. So this is why we need to do the control. Then the question is how to add in the additional transfer function, or how to determine the best parameter of existing feedback control loop, all right, so that the system will give a better result or behave very closely like a static system. Understand? Okay, so here I'm going to showing you 4 design methods, the typical design method. All right, so these are the core of control theory, all right? So in 10-20 minutes, so you gain exposure to this very powerful, useful design method in control theory. First one is for us to design stable control system. The question is how to determine the value of a certain parameter, all right, so that the system will be stable to achieve stability. So design method 1 is to achieve stability. So input to this method is the transfer function of equivalent, is the equivalent transfer function of the closed loop control system. So here I just write it down. Assume this is a transfer function of a closed loop control system. Then we just focus on the denominator. Normally, denominator is a polynomial equation of degree n. Then we use this to build up this Rouse array, all right? Because we have a term S with the power n, S with the power n minus 1. Here, you just imagine we have a S with the power 0. Then we form a row with n plus 1 row, because the first row is Sn with power n. Second row is S with n minus 1. Last row is S with power 0, right? Then we use all the coefficient to fill up the first two rows in the zigzag way, because this is a Sn minus 1. Sn minus 1 is here. So in a zigzag way, okay, in a zigzag way, all right? So fill up the first two rows. Then use this formula to calculate the element in the remaining matrix, all right? So this is a Rouse matrix. Then how to determine this value? So we use the previous two rows, okay? And pick up the value in the first column and the two value from the column after this column. So in this case, first column, always first column, these two value. Then column after this column is these two value. Then use this 4 value to do this calculation. That means this one times this one minus this one times this one divided by this one. All right. So is this formula. In case you are here, then you will take these two value plus these two value, then you apply this formula. Then you fill up all the rest element. All right. Here I showing you one example. You see, you have this denominator. This is a denominator equation. We just use this one. Okay. Then we form a matrix of 5 rows. Row S1, row S0, S1, S2, S3, S4. All right. Then fill up the first two rows with this coefficient in a zigzag way. 1A, 32, 80, 100. Then you apply previous formula to calculate all the value in the remaining element. And the empty location means 0. 0, you do not need to write 0, 0, 0. All right. Then conclusion is when all the elements inside the first column have the same sign, that means there's 0 change of the sign, then this system is stable. Then we use this conclusion to serve as a design tool to determine the value of a certain parameter, which will make the number of a change of the sign in the first column to be 0. That's it. All right. So this is a very simple tool. And for example, in this case, you will encounter unstable system. All right. So you build up a Rouse array. Then you see there's a 2 change of a sign, positive to negative, negative to positive, then 2 change of a sign. All right. So this system is not stable. All right. So we apply this method to design control system which will be stable. And here I just show you a simple example. For example, we want to know how to select the value for K, which will make my control system stable. All right. If let's say your customer want to know, okay, how to choose a value for K, then you say, don't worry, okay, you do a little bit of calculation. First, you build up this Rouse array, right? So you have a 4 rows. The first 2 rows, you use a coefficient of a polynomial equation to fill up. Then you apply the formula of a Rouse array. This is the formula of Rouse-Hurwitz criteria equation to determine the remaining element. For this system to be stable, that means all the value inside the first column must be positive, because the first one is positive, then the rest must be positive, right? Then you have a 1 plus K positive, this guy positive, this guy positive. Then from these 3 conditions, immediately you know for these 3 conditions to fulfill, then K must be smaller than 1 from this one, and K must be greater from this one, means that K must be greater than negative 1/3. Since the question tells you the K is positive, then K can only be a value within 0 and 1. Then you tell your customer, say, choose a value K within the interval between 0 and 1. That's it. All right. So, and then if let's say you choose K to be 1, then what happens? If you choose the K to be 1, this is a special case. Then you encounter 0, 0. You see this row 0, 0 here, because when k equal to 1. When you see 0, 0 means this polynomial, use these two coefficients, you build up a polynomial. This polynomial will be part of this equation, right? Then you use this polynomial to compute first order derivatives. Then you get a new set of a coefficient to replace 0, 0. Then you continue the calculation, all right? So because you have a 0, 0, then you have use these two coefficients to build this auxiliary polynomial. Auxiliary polynomial, then you compute first order derivative, then you get this polynomial with 4, 0. Then you replace 0, 0 with 4, 0, then you continue the calculation, all right? Then from here, you see this system is stable, all right? Since this one is part of the initial polynomial or denominator, then we can compute the root of this polynomial, because this is a simple polynomial. Then the root is like j omega. This is then you will see, for those of you, if you know the control theory, this means there's oscillation. So it means in time domain, we have a sine cosine function. Sine cosine function is oscillation. It should be good enough for you to know, okay? Basically, when you see omega, means there's a presence of a sine omega. Good enough already. So you remember this Euler equation, all right? So e raised to the power j omega t equal to cosine omega t plus j sine omega t. It means once you have omega, okay, then in time domain you have omega t, okay, something like that, sine omega t, all right? So sine omega t means what? You have oscillation, okay? So this is some additional knowledge for you to know, okay? Then second method is to design control system with the desired performance, all right? So that means in the frequency domain, you can make the root of a denominator to be at a specific location. So here, if you follow my recommendation of considering S as a vector, so then this means this is the desired location for S, right? And we can use the transfer function of a second order dynamic system, okay? So this is a standard transfer function of a second order dynamic system. So it will look like this. And the inside here, you see, we only have a two parameter. One is zeta, another is omega n. Then, and actually, if you want the desired root, the solution, because if you solve this denominator, then you find the solution. Solution of a denominator, we call it as a root of a denominator. So this is the desired root, okay? And then you understand what does it mean by omega n. Omega n is the distance from the origin to the desired location. Then what is the zeta? Zeta is equal to cosine theta. Theta is equal to this angle. Let's say, so this one help you to visualize the meaning of this equation. Then from design point of view, as a designer, you can choose any location here, okay? Once you choose any location here, then actually you can calculate what is zeta, what is omega n. So that is a design philosophy. So this is a very simple mathematics, all right? So by having different type of zeta, you will have a different kinds of a response. But this slide help you to understand that the best value for zeta is 0.7, right? Because 0.7 is a very good response, all right? So normally choose it to be 0.7. And here you will see if zeta is smaller than 1, you have an overshoot, and you have rising time, response time, etc. All right. So then we can compute, determine the formula for us to calculate what is the first maximum overshoot, what is the time for the maximum overshoot to occur. Then what is the time for the output, the steady state response to enter into the error band of a steady state response. We can define the error band of 2%, 5%. Then the time for the output to enter the error band could be calculated in this way. So these are the very useful formula for you to transform design specification into the value of an internal parameter. So, okay, and then this is additional information for you to know. If let's say we want to control steady state response to be within upper limit, lower limit, all right? For example, so we set this upper limit, lower limit. So this just for you to know, okay, this is a process control. Then for motor control is a servo control. Servo control means the value can change, all right? Normally for temperature control is process control. Make sure temperature is within the limit or pressure within this limit. Then for motion control is a servo control. That means you have any equation for the output of the motion. Okay, so this just for you to know. And the hardware of a controller actually will allow you to do the configuration for the setting of doing process control, right? Okay, and when something goes beyond, go outside. So this is a let's say, okay, for this one, if this is within the control limit, upper limit, lower limit, there's no alarm signal, no interrupt or no signal. Once you go outside, it will trigger the signal, all right, etc. So that means the hardware will automatically help you to monitor whether it's a steady state response, right? Because here is just to have a steady state response, all right? Steady state response must be within these two values, all right? If it does not within these two values, then hardware will tell you, send the alarm signal, etc. Right? So now I use this simple example to illustrate to you how to make use this second method to do this design. All right? Okay. So for example, we want the maximum overshoot to be 5% and the settling time to be 2 seconds and the error band is 2%. Then immediately you know we apply the formula overshoot 5%. 5% means what? 0.05. Then you apply this formula. Then this is a simple equation that we need to calculate what is the zeta. Okay, so both sides we calculate, compute the logarithm function with the base value of e. Then you get this one, and the list has this value. Then both sides we raise the power from 1 to 2. Then this become pi square and the zeta square. Then this become a 1 minus the zeta square. Then we have a single variable of a zeta square. We can calculate what is the zeta square. Then once you know the zeta square, you compute square root of a zeta square. Done already. All right. Since we know the settling time is 2 seconds, error band is 2%, then the formula is this one. We know zeta. All right, then we can calculate what should be omega n. So you see, now we know zeta, we know omega n, then we know what should be the transfer function. Done already. So this is a very powerful, simple design method. All right, and one more example. This is a typical control loop of a motor, right? So inner velocity control of the motor, outer position control of the motor. Then we can write down what is the equivalent transfer function of the inner loop, then what is equivalent transfer function of the outer loop, then looks like this. Now immediately we want to know what should be the value for k and the small k, all right? So this is a design method, and the requirement is to have a damping ratio, zeta equal to 0.7, omega n equal to 4. Very simple, John. Then once you have this transfer function, immediately you understand that k equal to omega n square, and 2 plus kk equal to 2 zeta omega n. Question tell you what is omega n, what is the zeta. Then immediately you compute what should be the value for capital K, what should be the value for smaller k. All right, done already. All right. Then the third method is PID controller. This is useful, very powerful in case if you cannot achieve a desired output with the tuning of existing parameter inside your control system. Then you add in additional transfer function. So this is a added transfer function by you, all right? Then you determine the best value for these 3 parameters. Then you should be able to achieve any required control performance, all right? So why we call it as a PID? Because this is proportional to error. This is proportional to the integration of the error, proportional to the derivative of the error. So you see proportion, integration, derivative. So it's a PID, all right? So like that. So I use this example to illustrate how to make use of a PID controller, okay, to achieve the design. For example, you have this control system, then initially this is just a P controller, it's a constant. Then we have a certain error for steady state error. Now we want to reduce steady state error to be 0. Then what should be this controller? Is it possible to achieve 100% accuracy? And also, if there's a disturbances here, it's possible to cancel out the influence of these disturbances, make the output, a steady state output from these disturbances to become 0. So it's magic, John, to achieve 100% accuracy even when there's a disturbances. All right, so you will see it's very simple to achieve this with PID controller. All right, first, now here you see we consider this is a 2 input single output is MIMO system as a sum of a 2 SISO system. When we study this one, we just ignore disturbances. Okay, so we separate them. Okay, we have a 2 control loop. Okay, of a SISO, single input, single output. Then what is the equivalent transfer function for forward branch 1 minus the loop transfer function? Simplify it, you get this one. All right. Then from here you can, because the input is unirun means a t square. Once you have, is a t, okay, it's not the 1. 1 is a unit step. Unirun means a time domain. The input is equal to t. Then in frequency domain is 1 over s square. And then because we are able to determine what is the transfer function for the error, because this is a transfer function between input and between output and the input. Then what is transfer function between error and the input? Because error is equal to input minus output, then input divided by input equal to 1. Then we have output divided by input. This is simple mathematics you can follow. Then because this one is equal to this one, then substitute this one with this one, then merge these two together, you get this one. So this is a transfer function between error and the input. Once you know Laplace transform of the input, then this one times this one give you Laplace transform of error. Okay, then we use the final value theorem to determine what is the steady state response of error. So then S times Laplace transform of error. Laplace transform of error is equal to transfer function between error and the input times Laplace transform of the input. Then you simplify it, then you get this result. If this one is a constant and we want the error to be within 0.1, then what should be the k? Then 2 divided by k equal to 0.1. That means k must be greater than 20. If it's bigger than 20, then error will be smaller than 0.1. Now the question is, when k is a constant, there's no way for you to make 2 divided by constant to become a 0. There's no way, John. It's always something there. Now you see the magic with PI controller. All right. So how to make this guy to become 0? Answer is very simple. Use PI controller, because this is a integration in frequency domain become a 1 over s in time domain. All right. Then you merge these two together, replace the k by this one. And with this equation, you will see, regardless what is the value of a k1, k2, when s converges to 0, because 0 times anything is equal to 0, then you get the 0. Magic, John. Okay, so you can choose any value for k1, k2. Final error always 0, 100% accuracy. Then how's about the power to cancel out the disturbances? Now we look at this relationship between disturbances and the output. Again, we write down the transfer function. Then from this transfer function, we should be able to know what is the Laplace transform of output, which is equal to transfer function times the Laplace transform of disturbances. All right. Then we apply final value theorem. So S times Laplace transform of output, which is equal to Laplace transform of this Laplace transform between output and the disturbances times Laplace transform of disturbances. All right. you simplify it, you get this one. How to make this one to be 0? We just choose a PI controller. Let Ks equal to K1 plus K2 divided by S, all right? Then Ks equal to this one. Replace 1 over K by 1 over this one. Then you get this one. You see, regardless what is the value of K1, K2, this is always equal to 0 because 0 times anything equal to 0. Magic conclusion is what? With PI controller, we can achieve 100% accuracy. All right. The fourth method is root locus method. Right. Root locus method is to A-in Dirac compensator, or there are two situations. One is if you are lucky by choosing the value of existing parameter, you can make the actual root to reach a desired location. And this one is basically to visualize all the possible root of a denominator in the S-plane by changing k when it varies from 0 to infinity. Then it's like this red line. When k varies from 0 to infinity, then you visualize the entire location of the root. And if this curve pass through desired location, then you are lucky, done already, all right? Because you just find the right value, okay, for k. If you are not lucky because this one does not pass through desired location, if let's say I want the root to be here, let's say to be here, which is not on the red line, then what are we going to do? The good news is to A-in Dirac compensator, all right? Then if you modify the curve, then let this curve to pass through a desired location, all right? Then how to achieve that? So here just showing you an example. If let's say we have this transfer function of feedback control root, and the k parameter is here. Now we want to know, okay, when k varies from 0 to infinity, how is the curve looks like, all right? So we just focus on the denominator, all right? Then we do a little bit rearrangement because we want to make a k to stand out, right? Then in this case, we express because we always want to write the denominator in this way, 1 plus k times something, all right? And here is not the 1 plus k times something, it is k times s plus something, all right? So we do this manipulation, then both sides divide by this, then you will get the 1 plus k times something. Then we consider this as a new open loop transfer function, right? Because GS here is forward branch transfer function. We also call it as an open loop transfer function, all right? And this is a closed loop transfer function, okay? This ratio put together is a closed loop transfer function, all right? So then this is the equivalent. Then we can let the k vary from 0 to infinity. Then you apply library function, it will automatically draw the root locus for you, all right? So here I just play this video to you. And then the good news is MATLAB has a full support for you to use Laplace transform. Then it's good for you to make use of a MATLAB. Then you can easily design a control system with a root locus method, right? So here I just key in open loop transfer function. So this demonstrates to you how to use MATLAB. You can follow this video to learn how to use MATLAB, right? Then there's a magic function, root locus, okay? Input open loop transfer function. Press enter, then it draws for you automatically, right? So you see you have a 4 curve. So it means you have a 4 root, all right? So then different color. Then if let's say you want your root to be here or to be here, then you know what should be the value. But for this system, you see the root enter the right half plane. When the root enter right half plane, basically means he has a positive horizontal component. When it has a positive horizontal component, then you have a positive power for the exponential function, e with a positive power. Once you have a positive power, And when t go to infinity, then this value go to infinity. It means what? The system become unstable. So it's very easier to understand. All right. So we should not have a positive horizontal component. That means the root must remain in the left half plane. All right. So obviously this is not a stable system. Right. So we move on. Then how to design? Okay, let me see. Then how to design a control system which will make an unstable system to become a stable system, right? So then we can use a Dirac compensator. So this is background knowledge. Let's say I want the root to be here. So basically we want the omega n to be this value and the zeta to be this value, all right? So this is a design specification. Then you have a two situation. One is you are lucky, then you just find the value of existing parameter of k. And the second situation, you are not lucky, then you need to insert a compensator. This is a Dirac compensator. That's it, all right? So now I'm going to show you an example for you to understand the power with this force method, all right? So we have this control system, assume like a motor like AGV. Then initially is not stable. Let's say we have a value k, which is 1, and then we ask you to draw how it looks like. Now, we want the root to be at this location, -1 plus minus G1. If we use a PD controller, what is outcome? If we use a Dirac compensator, what will be the result? Then talk about a little bit the improvement of your design solution, all right? So let's say initial system with a value 1 for k. Then you use MATLAB, you will see you have oscillation. So this is not the stable system, all right? Now we use a PD controller. D means a derivative. Once you see a derivative, you have an S. Then in frequency domain, controller is K1 plus K2S, all right? Because now we insert this one is K1 plus K2S. Then we can compute what is the equivalent transfer function for forward branch 1 minus loop. Simplify it, you get this one. Since we want the root to be -1, 1, then we know what should be the omega n. Omega n is this distance, so it's equal to square root. Omega n equal to square root 1 square plus 1 square. We also know what is zeta. Zeta is equal to cosine 45 degree. Zeta is equal to cosine 45 degree. You see, you know already. Once you choose desired root, immediately you know zeta omega n. Then Kp is omega n square. Kd is 2 zeta omega n. All right. So 2 zeta omega n. So this is a design method 2. All right. So we follow design method 2. Actually, it's a combination of design method 2 and 3, because 3 use a PD controller. 2 use a standard transfer function of a second order dynamic system. So this is a hybrid design method, all right? Then you can easily calculate what is KB, what is KD, all right? Then you can use MATLAB to verify how good is the control system. You see, initially oscillation, after design is very nice, all right? And response time, pay attention here, more or less 3.5 seconds, all right? Then how about the Dirac compensator? So we insert this Dirac compensator here, and here we just write down the denominator. So 1 minus loop transfer function, this is the denominator, all right? Then replace, substitute this GC by this Dirac compensator, simplify it. Then we have this polynomial equation of degree 3. Because we want the root to be here, because this is a complex root, then another root is here because it's a -1 plus minus G1, all right? So it means here it will offer you 3 root. 2 of them has been chosen by the customer because I want this system to have these 2 root plus minus -1 plus minus G1. Then there's a 1 remaining root. Then we can use this one, okay, to determine what should be the best value for Z and the P. So then means this one must include these 2 root plus additional root. So we expand them. For these 2 equations to be equal means what? Their coefficient must be equal. So immediately you know that the 2 plus P0 must equal to this okay, K is here, 2 plus 2P0 must equal to K. And P, and then in this way, both sides divide by 2, then you can get the P0 equal to K divided by 2 minus 1. Okay, you get the what is P0 in terms of K. Then how to determine the Z? So it's KZ equal to 2P0. So KZ equal to 2P0, right? So then immediately you know that, okay? Because the P0 is equal to 0.5 K minus 1. Then replace this one by this. Then you get the KZ equal to this. Then both sides divide by K. Then you get the Z. How to determine P? Because P equal to 2 plus P0. P equal to 2 plus P0. Then replace P0 by this result. Then you get this answer. Now we know P is a function of K. Z is a function of K. Then we have this controller. All right. Then we want to know how to choose a K. We just choose a 3 value, all right, quite easily. So here we just choose a value for K to be equal 2.0, 2.5, 3.0. Then use MATLAB to see the output. From here you will see K equal to 2.0 will give you a very good result, all right? So then this is a design solution, all right? Okay, so then this video showing you the demonstration in MATLAB, all right? So with the 3 value for K, then we have a 3 transfer function, open loop transfer function, closed loop transfer function. Then we call this step, magic function step, right? So then he will show you the time response. Then you can judge which one is better, okay, which one is desired one for you, all right? Okay, that's all for the lecture 3. So in lecture 3, basically, we go through the key content or the major design method in control theory. You can apply these 4 design methods, okay, to design feedback control loop for your motor or for your temperature control loop or force control loop, all right? So first design method allow you to design a system which will be stable. Second design method will allow you to design a control system with a desired control performance, all right? And in case by tuning the existing parameter, you are not able to achieve the control result, you get A-in PID controller or A-in lead-lag compensator controller, right? So then by now, we complete the study of section 1. So if let's say we do a quick summary about what you have studied from today's lecture. So it's quite straightforward. So in today's lecture, you know what is a manufacturing system, what is a production system, what are the popular process which could be under control automatically, and what are the important variable or parameter which could be controlled automatically, all right? And among all these controllable parameter and variable, you understand that the motion related parameter are very, very popular, all right? Therefore, we know that we can apply the 4 design methods in control theory to design the control system for motion control, the control system for temperature control and the pressure control, etc. And the additional knowledge for you to know is the design method in control theory make use of equation in frequency domain, because equation in frequency domain is much, much simpler than equation in time domain. That make you understand why control theory will use Laplace transform, because a lot of students has a trouble to understand, okay, why Laplace transform, okay? So once we have a control system, then we have an automation system. Once we have an automation system, then we have an advanced manufacturing system, all right? So now you have a good understanding about what is industrial automation, all right? Because inside the industrial automation, we have an automatic control system for motion, for temperature, for force, All right. Okay. Since we ran out of time, you try to digest today's lecture, formulate your question, and next week we are going to do session 3. At the beginning of section 3, we will do a short Q&A session, and during the Q&A session, you can raise your question, and then I will try to answer your question. All right. Okay. Thank you for your attention, and have a good weekend.